Dijkstra's algorithm offers a solution to the shortest path problem. I'll use this video to explain the algorithm and show an example of how it works on a certain graph. So the graph I'm going to use comes from the town I grew up in, Vienna, Virginia. And growing up, it was a point of contention in my family. What was the fastest route from our house to the town's main street? Should we take the back roads or the main roads? So my family's house was right about here at point A, and the main drag was right where this Crumble Cookies is. Now you can take the main roads and get there a pretty straightforward way, but there are a lot of back roads ways that you might take to get there as well. So we'll go ahead and highlight a few reasonable routes that you might decide to take to get from point A to point B. There are other possibilities as well, but let's focus on what we have here. If we're hoping to model this as a graph, I've sort of already shown you the connections, but I'll put nodes at all of the intersections. And as we've seen in graph theory, the exact locations and arrangement of the nodes is not exactly what's important. What's really important is just the nodes themselves and the connections that exist between them. So I'll just work with the picture on the right here. So if we're looking for the shortest route from A to B, let's say by time, then we sort of need to know how long each of these edges takes to drive. So for the purposes of this problem, I'll make some guesses here. So as you can see, even though this is a small town and there's really only a handful of routes among the many that you could choose highlighted, it's still a somewhat complex problem. It's not obvious which route is going to be the fastest from this picture. If I asked you to solve this problem without really knowing an algorithm, what you might think about doing is starting at point A and then just trying a few things, maybe branching out from each of these sort of early on nodes that you would reach from A and testing out different ideas about how you might get from point A to point B, and just how to branch out from one node to another as you go. And that's generally the idea behind Dijkstra's algorithm, but we do need a protocol to stay organized. This will help us make sure that we don't accidentally miss some fastest route, and also make sure that we don't repeat our work. So I'll start describing Dijkstra's algorithm and use this graph on the right as an example. So the input for this algorithm is a edge-weighted graph with two nodes. And the output should be the shortest possible path between the two nodes. So in the algorithm, I'm going to classify the vertices into three categories. There'll be the unvisited nodes, there'll be the current node, and I'll highlight the current node in red, and then there'll be the visited nodes, and I'll highlight those in green. So all of the nodes will start out as unvisited, then each one will eventually become the current node, and after we're done with that vertex, it'll become one of the visited nodes. All of the unvisited nodes, I'm going to assign to them a tentative distance. Think of this as the shortest distance that we've found so far from A to that node. For the current node and the visited nodes, I'll assign these a final distance. So by the time a node becomes the current node or visited node, we'll be sure that we know the shortest distance from A to that node. And so at that point, the distance that I assign will no longer change. So let's go through the steps of the algorithm. First, I'll use the start vertex, in this case vertex A, and I'll call that the current vertex. And I'll mark its final distance as 0. All the other vertices are unvisited. So since vertex A is the current vertex, I'll color it red. I'll leave all the others black since they're unvisited. Since it's a current vertex, its distance is final. And it's no surprise that the distance from vertex A to itself should be 0. Okay, step 2 is the complicated one. It says for each unvisited vertex V that's connected to the current vertex, find the following sum. The distance for C plus the weight of the edge from C to V. And then I'm going to update the tentative distance of that vertex V if needed. So it's easiest to see this in an example, so I'll go through this for the example that we have here. So our current vertex, vertex A, has two neighbors, the one above it and the one just to the right. So I'll start with the vertex above. So in calculating this number x, it's supposed to be the distance of the current vertex, so that's 0, plus the weight of the edge. So that's 0 plus 2, which is 2. So I'll label that vertex with a tentative distance of 2. Notice that I also highlighted the tail of the edge that I used to get there. I'll do the same thing for the other vertex here. I need the distance of the current vertex, which is 0, plus the weight of the edge, which is 1. And so I'll label this vertex with a 1, and that will be its tentative distance. Okay, I've gone through all of the vertices that were connected to the current vertex, and so I'll go on to the next step. This says to mark the current vertex, the one in red, as visited. So I'll go ahead and change it from red to green. And then the fourth step says mark the unvisited vertex with the smallest tentative distance as current, and then repeat from step 2. So in this case, the unvisited vertex with the smallest tentative distance, well, some of them don't have tentative distances yet, but the one with the smallest is the vertex right here, labeled with a 1. It's smaller than the one labeled with a 2. So I'll go ahead and color that one as red, since it is now current. Now, current vertices have a final distance, not a tentative distance. So this number 1, I'll go ahead and change to green. So changing it to green indicates that there's never going to be a shorter path to this vertex, this current vertex, than the one that I've already found. That going from A to this vertex, I could never get there in less than 1 minute in this case. So now I need to go back to step 2. So now that this red vertex is my current vertex, I need to worry about all of the unvisited vertices that are connected to it. And there's 2 of those. There's the one right above it and the one up here. So for the one right above, I need to use the equation. It says the distance of the current vertex, which is 1, plus the edge, which is 0.5. And that's the label of the tentative distance I'll assign to this vertex. So that'll be 1.5. And again, I'll highlight the tail of the edge we used to get there. For the other vertex connected to the current vertex, I'm going to take the distance of C, which is 1, plus the weight of this edge to get there, so 1 plus 2. I'll label this one with a 3. Okay, now I'm on to step 3. I can label my current vertex as visited. And now I need to choose the unvisited vertex with the smallest tentative distance. So there are 3 unvisited vertices with distances, tentative distances already. The one with the smallest tentative distance is this one right here. So I'll go ahead and color it red, and I'll change its tentative distance into a final distance. This tells me that I know the shortest distance from A to the current vertex. It has to be 1.5. I'll never find a shorter route to get there. Okay, from my red current vertex, there are 2 unvisited vertices connected to it. There's the one right above, and this one's also still unvisited. So I'll go ahead and calculate this x for each of them. So for the one up above, I'm going to take the distance of the current vertex, 1.5, plus 1. So this vertex gets a tentative distance of 2.5. That's the shortest distance we've found so far to this vertex. Now for the other vertex over here, I'll do my current vertex, 1.5, plus the 1 minute over here, so that's going to be 2.5. So this is different than the old tentative distance of 3. And what the instructions say is that if the new x is less than the tentative distance that's already there, you should update it. So my 2.5 is less than 3, so I'll go ahead and get rid of the 3 and update that to 2.5. You can see that I've also changed the indicator of which way I came from in order to get that 2.5. What it means when I do this updating is that I've found a shorter route to this vertex here. Originally, my shortest route was the one I'm showing here, but now I've found a shorter route, the one that goes first to the right, then up, and then to the right again. Okay, I've finished with the current vertex, and so I'll move on to step 3. I'll mark the current vertex as visited. Just change its color to green. Now I'll look for the smallest purple number, the smallest tentative distance, which is the vertex up here, the 2. So that becomes the current vertex. Its tentative distance becomes a final distance. I'll never find a route to this vertex right here with distance less than 2. And I'll cycle back to step 2 of my algorithm. So there are 2 unvisited vertexes that neighbor my current vertex, the one all the way up here and the one just to the right. For the one up top, I'm going to take the 2 plus the edge weight of 2 and get a total of 4 as the new tentative distance. Once again, I'll highlight the tail of the edge I took to get there. And looking at the other vertex to consider, if I take 2 plus 0.5, I get 2.5 again. So I don't need to update that. I can just leave it as 2.5. What that means is that the original route I took to get to this vertex, well, I can trace back these little tails that I've highlighted. The original route that I took to get here was, well, I'm going backwards, but let me go forward. Start from A to the right, up, and up. That was 2.5, as it was 1 plus 0.5 plus 1. But the new route that I just discovered was going up to my current vertex and then over. 2 plus 0.5. Both of those have a distance of 2.5, so there's no need to update. All right, I'm done with my current vertex, so I'll change it to green. And I now have 2 lowest tentative distances, 2.5, so I'll just pick one if it's a tie. And I'll go ahead and pick the one right here. So its tentative distance becomes final. And there's only one unvisited vertex that is connected to this one. It's the one right here that's labeled with a 4. Well, using my equation, the distance for the current vertex plus 1 gives me 3.5. That's less than the 4. And so I'll go ahead and update it. And change the indication of which way I came in order to get there. So since I came from the current vertex, I'll change the highlighted edge. Okay, we're done with our current vertex, so I'll highlight it green so it's visited. Now the lowest tentative distance that I see is the 2.5 down here. So I'll mark that as current and change its distance to final. The current vertex is connected to 2 unvisited vertices. For the one right above, I have 2.5 for the current plus the 2.5 minutes in between, so that'll be 5 minutes total. For the other vertex, which is actually my endpoint B, it takes 2.5 minutes to get to the current vertex, and then another 3 minutes to take this edge. So that's 5.5 for the vertex B. Now I'm not finished yet because B has not been visited. This is only a tentative distance. I might find a shorter distance to get to B. I'm not done until the distance on B becomes a final distance. I am finished with my current vertex though, so it'll become visited. And among the unvisited vertices, the one with the smallest tentative distance is this one right here. So I'll change it to red as the current vertex and change its distance to final. It's only connected to one unvisited vertex, and we can say that The current vertex, it takes 3.5 minutes to get there, plus 1 is 4.5. And that's less than the current tentative distance, which is 5. So I'll go ahead and change it. And of course, I'll change the indication of where I came from to get that 4.5 as well. Okay, I'm done with the current vertex, so I'll color it green for visited. And between my two unvisited vertices, the 4.5, the one right here, has the lowest tentative distance, so I'll make that my current. And change its distance from tentative to final. The only unvisited vertex left is connected. It's point B. And if I calculate x, it ends up being 4.5 plus 1.5, that's 6. However, 6 is not less than the tentative distance we'd already found. So I'll go ahead and keep the 5.5 that we had before. Okay, I'll finish it out. Our current vertex becomes visited. The last vertex B becomes the current vertex. And there are no unvisited vertices left, and so I'll just turn B to visited. And so this distance of 5.5 is the length of the shortest path from A to B. And since I highlighted the tails of the edges that took me there, I can retrace my steps and figure out what that shortest path was. I'll go ahead and highlight, starting from the end actually, and going backwards, and then we can see what that shortest path from A to B was. So because of the systematic approach here, Dijkstra's algorithm always finds the shortest path from A to B. We might say that Dijkstra's algorithm is optimal. And also because of the systematic approach, it ends up being pretty fast, at least for a computer. We'll do another example and some analysis of the algorithm in the next couple of videos as well.